So first of all, I wonder, why do we need robots to plant trees? What problems can it solve?
The biggest problem for our planet is global warming and climate change. There is very most effective way to fight climate change is planting trees.
In one of the harshest, driest regions on Earth, something extraordinary is unfolding. A once hopeless stretch of shifting dunes is now the stage for a silent, high-speed revolution. No, this isn't science fiction. It's happening right now, and it's defying everything we thought we knew about environmental recovery. The transformation is so massive, it's visible from space, and yet most people have never even heard about what's driving it. These aren't your average machines, and they're not just planting trees. They're changing the rules of nature. Stick around, because what's happening deep in China's most unforgiving desert is more unbelievable than you can imagine. China's desertification origins. By the late 20th century, China faced one of the most severe land degradation crises in the world. An astonishing 2.61 million square kilometers of its territory, nearly one-third of the nation's total land area, had succumbed to desertification. This environmental challenge posed not only an ecological threat, but also a significant socio-economic burden, particularly for regions reliant on agriculture, livestock, and sustainable rural livelihoods. Entire provinces were affected by encroaching sands, shifting dunes, and degraded soil that could no longer support traditional farming or habitation. At the heart of this crisis lies the Taklamakan Desert, one of the most formidable natural obstacles China has ever faced. Covering roughly 330,000 square kilometers, it is Asia's largest desert and the second largest shifting sand desert in the world. Often dubbed the Sea of Death, its dunes are not only vast, but extremely mobile, some shifting dozens of meters overnight. This constant movement threatens nearby transportation routes, undermines infrastructure, and frequently buries farmland under layers of sand, making the surrounding region highly vulnerable to ecological collapse. The root causes of China's desertification process are entrenched in both environmental and human dimensions. Excessive overgrazing in arid and semi-arid areas denuded the land of its protective plant cover, leaving the soil vulnerable to erosion. Decades of deforestation caused by logging and agricultural land clearing added to the instability of the ecosystem. Added to these problems were erratic climate fluctuations, particularly severe droughts and shifting rainfall patterns, which sped up soil degradation and desertification processes in northern and western China. The combination of natural vulnerability and unsustainable land management created a feedback loop that converted previously productive land into wind-blasted deserts. As communities were forced to the brink and ecosystems collapsed, the Chinese government had no choice but to meet the desert head-on. This tipping point set the stage for one of the most ambitious land restoration and desertification control efforts in history, foreshadowing future innovations such as robotic afforestation and eco-barrier construction. But before high-tech machines took over the fight, an army of determined humans faced the desert with grit, hay, and hope. Early manual desert control. In response to the escalating threat of desertification, China launched the ambitious 3 Norths Shelter Belt project in the late 1970s. This monumental ecological initiative aimed to create a massive green barrier stretching across the northern, northeastern, and northwestern regions of the country. Designed to halt the spread of deserts like the Taklamakan and Gobi, the project mobilized an unprecedented scale of resources. More than 200,000 workers, including civilians, scientists, and even military personnel, were dispatched to remote desert frontiers to begin the painstaking work of land restoration. The initiative marked one of the largest afforestation campaigns in human history and represented China's early commitment to long-term ecological stability. One of the oldest and most successful methods in these early manual endeavors was the establishment of straw checkerboard grids, easy yet efficient structures created by burying blocks of hay in a grid formation. The grids would be used to pin down the sand, lower the erosion caused by wind, and retard the advance of dunes. In conjunction with this, Chinese horticulturists also brought with them specially cultivated drought-tolerant flora that would thrive in dry environments with the minimum amount of water. These robust species, once established, further served to stabilize and initiate the process of ecological recovery. Primitive by today's standards, these low-tech manipulations represented the bulk of China's early desertification control. Despite the innovation and dedication that went into these early techniques, they were seriously constrained. The labor was slow and backbreaking. Workers could typically cover only a few hundred square meters of sand stabilization per day in grueling conditions. The deserts were far from any major centers. Transport was bad, and climatic conditions were extreme, with blistering daytime temperatures, freezing nights, and regular sandstorms. Water and shelter were in short supply, and the workers suffered physically to a great extent. In such circumstances, even limited advancements demanded too much effort and determination. Additionally, the manpower, materials, and logistics expense of massive expansion proved impossible to maintain in the long term. Though the fruits of the efforts were tangible, tens of millions of trees planted and sections of the desert stabilized for the short term, the rate of change overall was modest. The magnitude of China's desertification issue dwarfed what was within the feasible scope by hand. These challenges eventually vindicated the necessity for mechanized solutions and, consequently, the progressive introduction of automation and, eventually, the use of robotic technology for desert control. The technological leap. China's journey into robotic desert control began in earnest in 2021, when early research and development efforts were initiated to find technological solutions for land degradation. Scientists and engineers recognized that the traditional, labor-intensive methods were no longer sufficient to combat desertification on the scale and speed required. Initial prototypes of desert control robots were field-tested in some of the most challenging environments in the country, including regions surrounding the Taklamakan Desert. These early trials aimed to determine whether machines could operate effectively in extreme heat, shifting sands, and remote locations while carrying out tasks like soil preparation, seed planting, and irrigation. With the success of the initial tests, China stepped up development by investing in a vast range of specialized desert control equipment. In the following years, scientists developed and perfected over 150 various models of machines, each designed to carry out precise tasks required to restore the ecosystem. These were drilling machines for making holes to plant, robotic irrigation units, terrain navigators, and AI-powered visual analyzers for finding the best sites to plant. This iterative development cycle was directed by feedback from on-the-ground operations in the field to ensure that every new generation of machines was more suitable for actual use in demanding desert environments. By 2024, China had achieved a technological breakthrough that allowed for the large-scale deployment of desert control robots in multiple priority desertified areas. This phase entailed not only the mass production of the robots, but also building the requisite logistical infrastructure to enable them to function. Production facilities were increased to accommodate orders, and local training facilities were constructed to help technicians and operators efficiently maintain and operate the systems. Their incorporation into the overall 3 Norths ecological scheme was a revolutionary break with conventional methods of restoration and saw a new, entirely mechanized, information-based paradigm of land regeneration. This technological jump enabled China to increase the scale and speed of its desertification control efforts dramatically. The synchronized operation of thousands of robots greatly lessened dependence on human labor while enhancing precision and uniformity in afforestation. These robots were able to operate continuously in harsh conditions, traverse large areas efficiently, and adjust to uneven terrain through intelligent navigation systems. The creation and deployment of desert control robots marked a new frontier in ecological engineering, demonstrating the potential for innovation and the environmental need to spur large-scale technological solutions to one of the world's most intractable problems. How the robots work. At the heart of China's desert control robots lies a powerful AI-driven visual analysis system that allows each unit to make intelligent, real-time decisions in dynamic environments. These systems are equipped with high-resolution cameras and sensors capable of scanning the terrain to determine the suitability of various patches of land for tree planting. The AI analyzes multiple variables simultaneously, including soil texture, moisture levels, terrain elevation, and potential obstructions like rocks, gullies, or shifting dunes. This capability ensures that robots can avoid areas where seedlings are unlikely to survive, and instead focus planting efforts where growth potential is highest. By enabling this kind of on-site assessment, the robots vastly improve the efficiency and success rate of desert greening efforts, minimizing wasted resources and effort. Aside from terrain evaluation, the robots are automated to perform the whole tree planting procedure independently. Every robot has a mechanical drill that may insert deep planting holes quickly, usually up to 1 meter deep, and is designed to hold seedlings firmly in loose, sandy soil. After the hole is created, the robot adds a measured amount of water or hydration gel to aid in initial root establishment, then places a drought-resistant seedling with precise accuracy. This efficient process is completed in seconds and is repeated hundreds of times an hour, enabling each machine to plant as many as 160 trees per acre in 20 minutes. The capability of drilling, watering, and planting in one pass is a giant step forward from doing it manually, which took different crews and days to achieve the same result. Perhaps the most groundbreaking feature of China's robotic afforestation system is that it utilizes coordinated group behavior, much like a swarm of locusts or an armada of autonomous drones. The robots are programmed to work in groups, usually 5, employing a cluster-based control paradigm that allows them to divide and conquer immense desert territories with tremendous efficiency. Each team is connected to convey information regarding the terrain conditions as well as work progress, so that no location gets missed or redone. With this coordination, the robots also get to switch on the fly, dynamically varying their paths considering obstacles, work zones completed, or varying environment data. By working in unison, these swarms can cover up to 180 acres of land per day, a feat that would be nearly impossible through human labor alone. The swarm coordination model not only increases speed and efficiency, but also enhances reliability and resilience when encountering environmental issues. If one of the robots suffers a technical glitch or needs to stop for maintenance, others can redistribute its load and resume the operation with minimal interruption. Such inherent redundancy and flexibility make the system perfectly applicable to unstable desert environments where extreme weather and terrain fluctuations are the norm. With GPS monitoring, real-time feedback data, and machine learning software, the robots improve their performance with each passing day. China's desert control robots are, therefore, not simply autonomous planters, but a complete integrated, smart system that can turn empty deserts into lush green belts with precision and on an unprecedented scale. Operational scale and efficiency. Gains. China's deployment of 8,000 advanced desert control robots represents one of the most impressive examples of scale in ecological restoration technology to date. Each robot is engineered for speed and precision, capable of planting approximately 160 trees per acre in as little as 20 minutes. This level of productivity drastically outpaces traditional manual methods, where a small team of workers might require an entire day to complete the same task on just 1 or 2 acres. By automating key steps like soil drilling, watering, and seedling placement, these machines compress hours of labor into minutes, allowing afforestation efforts to proceed at an unprecedented pace across China's vast desertified regions. The effectiveness of such robots is still increased by the use of an organized operational methodology where they act in closely consolidated groups. Ideally, 5 of these robots will be used in a cluster where they operate jointly under a concerted control system, scanning large landscapes. In a day, it is possible to have such a team plant trees on as much as 180 acres of deserts. This method not only boosts the treated area per day, but also adds flexibility and redundancy to the process. When a single robot finds a malfunction or blockage, others can adjust in real time, and as a result, the overall process is not unduly affected. This combined capability is an important aspect of upscaling restoration activities across thousands of square kilometers. What really sets these robotic systems apart from previous strategies is the exponential increase in efficiency they provide. Comparatively speaking, robotic afforestation is over 10 times more rapid than manual labor. This production increase enables China to address scales of reforestation previously unimaginable, making decades-long tasks into accomplishments within a span of merely a few years. In addition to the planting itself, the robots also streamline supporting logistics. By minimizing the number of staff that required to work in severe desert conditions and removing much of the repetitive, labor-intensive work involved, operational risk and staff fatigue are reduced, while ensuring planting quality consistency. These gains in efficiency have not merely accelerated China's desert control aspirations, but have also made the nation the world leader in the science of mechanized ecological rehabilitation. The fact that the robots can run continuously in harsh terrain and under harsh environmental conditions makes them well suited for application in other parts of the world with similar desertification issues. As more countries watch the scale and success of China's robotic afforestation program, demand for such systems is likely to increase. In the end, the enormous operational capacity unleashed by these machines turns afforestation from a labor-intensive battle into a high-tech, viable solution to one of the world's most pressing environmental challenges. But raw speed and scale are only part of the story. What truly powers this desert-conquering force is the engineering brilliance behind each machine. Advanced engineering behind the robots. The desert control robots developed by China are engineering marvels built to withstand some of the harshest environmental conditions on Earth. Operating in desert environments like the Taklamakan requires machines to endure extreme heat during the day, where surface temperatures can soar above 50 degrees Celsius, as well as intense ultraviolet radiation and frequent sandstorms. These natural challenges are not merely uncomfortable, they are destructive to conventional machinery. To combat this, Chinese engineers integrated specialized materials and heat-resistant coatings into the robots' exteriors, ensuring that sensitive internal systems remain insulated and stable during prolonged exposure to sunlight. Components such as cameras, sensors, and CPUs are sealed within dustproof and UV-resistant housings, maintaining functionality even under relentless solar radiation and fine-grained sand infiltration. Another foundation of the robot's sophisticated engineering is mobility. Deserts are seldom flat or predictable. Moving dunes, loose sand, and uneven ground pose significant challenges to automatic navigation. In response, the robots are designed with high-traction systems and strong chassis, capable of 25-degree slopes and reliable operation on 12-degree inclines. They are able to do this by maintaining balance and traction while traveling over dunes, depressions, and hilly contours. Their treads and wheels are specifically engineered to stay gripped on uneven sand surfaces, and gyroscopic stabilization and live terrain feedback guarantee that planting operations are performed precisely even on slopes. These enable them to be very versatile in a variety of desert environments, not limited to flat basins. To remain operational around the clock, the robots are equipped with integrated cooling systems and highly durable mechanical frames. Desert temperatures drop sharply at night and spike during the day, and these thermal extremes could otherwise degrade performance or shorten machine lifespan. The internal cooling system helps regulate engine temperature and prevent overheating during continuous operation. Concurrently, their outer casings consist of corrosion-resistant metals and composite reinforcement materials, providing resistance against abrasion from blowing sand and shock loads from rugged terrain. Such durable bodies not only shield the machines, but also provide smooth planting cycles irrespective of environmental uncertainty. It has at its center a high-power engine and power module, constructed to provide long-duration energy and durability. There are some hybrid power systems present in certain models, which come with solar charging panels augmented by conventional fuel-based engines or batteries. In this hybrid process, the usage time is improved, particularly where there is low recharging support infrastructure in rural areas. Additionally, these engines are capable of powering mobility as well as advanced functions such as drilling and irrigation simultaneously without the sacrifice of efficiency. Combined, these engineering factors guarantee the robots will be able to operate for prolonged periods of time, complete delicate tasks, and endure the everyday abuse of desert landscapes, placing them not just as a convenience tool, but as critical resources in combating desertification. Ecological impact. The introduction of desert control robots has significantly improved the ecological outcomes of China's afforestation campaigns, particularly in terms of tree survival rates. Traditional manual planting in arid zones often suffered from low success, with many seedlings failing to take root due to poor soil conditions and lack of irrigation. However, the new robotic systems employ precision planting and soil analysis to identify optimal locations, combined with advanced techniques like irrigation-free seedling technology, which enhances early root establishment. As a result, tree survival rates in some desert regions have surged to 70 to 80%, a level previously considered unachievable in such harsh environments. Apart from tree survival, these initiatives have initiated a spontaneous recovery of impoverished soils, once depleted of nutrients and susceptible to wind erosion. Vegetation reduces surface temperatures, slows down the speed of the wind, and stabilizes sand, causing it to settle, accumulate organic material, and gradually regain soil structure. In much of the region, previously desolate tracts have come to be transformed into man-made oases with microclimates that sustain biodiversity. These green oases not only sustain trees, but also offer niches for insects, birds, and small mammals, bringing back life to landscapes that were long regarded as ecologically dead. One of the most significant effects of this change is the reversal of a centuries-long ecological trend. Previously, huge areas of northern and western China experienced the gradual but relentless expansion of deserts, sand advancing and people retreating, as the locals referred to it. Today, for the first time in anyone's memory, the trend has reversed. In much of the affected territories, satellite imagery and reports on the ground indicate vegetation pushing steadily back against the edge of the desert. This transformation represents a significant turning point in regional ecology, re-establishing a sense of environmental security for communities that were previously at the forefront of desertification. These environmental dividends extend far beyond appearance or symbolism. They equate to concrete gains in air quality, soil productivity, and climate resilience. The more vegetation coverage, the more carbon sequestration, which means fighting climate change on a larger level. Restored habitats are also more capable of holding water, decreasing the occurrence and intensity of dust storms, and enhancing agricultural and human settlement conditions. In doing so, China's robot-driven afforestation program isn't only preventing desertification, it's building blocks for a cleaner, more sustainable environmental future. Economic and logistical advantages. The deployment of advanced desert control robots has not only accelerated the pace of afforestation in China's desert regions, but also significantly enhanced the survival rate of newly planted trees. Traditionally, one of the greatest challenges in desert greening projects was the high mortality rate of seedlings due to water scarcity, poor soil quality, and extreme environmental conditions. However, with the introduction of irrigation-free planting technology, supported by intelligent water injection systems and site-specific soil analysis, these robots have achieved survival rates of 70% to 80%, a dramatic improvement over previous methods. This increase in survivability ensures that resources are used efficiently and that each planting operation contributes more effectively to long-term ecosystem regeneration. In addition to tree survival, the robotic afforestation system is directly responsible for the rehabilitation of eroded soils, an essential process in reversing desertification. Vegetation planting stabilizes loose, blowing sands, and young tree root systems hold the soil together, preventing erosion. In the long term, this aids in the buildup of organic matter, enhances soil structure, and facilitates microbial action, all vital building blocks of a productive ecosystem. These new plantations also serve as natural windbreaks, slowing down the speed and force of sand-carrying winds, thereby further safeguarding the surrounding area. In other areas, what used to be barren, dry plains have progressively become artificial oases, sustaining not only plants, but also the return of fauna and even small-scale farming. This change has caused a perceptible shift in the ecological balance of most desert edge areas. While desertification used to signify sand advancing and people retreating, numerous places now witness the reverse: green advancing and sand retreating. This is not merely symbolic, it is a reversal of years of environmental decline. Forest belts and grasslands now shield susceptible communities from the worst effects of desert encroachment, safeguarding farmland and infrastructure. As the cover of vegetation grows, microclimates are also being modified, with some regions experiencing higher humidity and slightly higher rainfall, developments that could further support ecological stability in the long term. The wider ecological benefits of these activities are hard to exaggerate. By restoring health to once ravaged areas, China is establishing an example of how technology and environmental science can be used together to address large-scale ecological issues. The ultimate success of these robotic systems is more than just planting trees. It is the establishment of self-sustaining green environments that need fewer human inputs in the long run. These regions are vital shields against land degradation, dust storms, and climate change, transforming what were previously environmental deficits into fertile landscapes. The robots are machines, but the heritage that they are creating is profoundly natural, restoring life, fertility, and resilience to the long-abandoned places that had been desolate. China's global desert role. China has emerged as a global leader in the fight against desertification, gaining international recognition for its large-scale afforestation initiatives and technological innovations. Since joining the United Nations Convention to Combat Desertification, UNCCD, in 1994, China has played an increasingly influential role in shaping global policy and setting the pace for ecological restoration. Its success in reversing desertification, particularly through the ambitious Three Norths Shelter Belt project and the deployment of 8,000 desert control robots, has positioned the country as a model for others battling similar environmental challenges. China's progress has been lauded by global environmental bodies, and it is one of the first nations to approach the UN's goal of zero global land degradation by 2030. Apart from reaching domestic benchmarks, China has proactively sought technology-sharing collaborations with nations throughout Africa, the Middle East, and Central Asia, where desertification is an issue of significant concern. Much of these territories shares similar environmental characteristics with China's interior deserts, such as scarce water resources, movable sand dunes, and high temperatures. By providing access to its robotic afforestation technologies, AI-based systems, and soil stabilization methods, China is assisting other countries in developing their own capacity for land restoration. Saudi Arabia, the United Arab Emirates, Mongolia, and Uzbekistan have all dispatched delegations to China to learn about these developments firsthand, and, in most instances, have shown interest in adopting or co-developing similar systems. China's international cooperation does not stop at bilateral relations. China has played a leading role in international fora and has provided many demonstration areas to promote its desertification prevention measures. In the 16th Conference of the Parties to the UNCCD, Riyadh in 2024, China's green technology and the successes of the Three Norths project took center stage. The forum, which was attended by over 100 countries' dignitaries and experts, provided China with the opportunity to share its ecological engineering achievements on a global platform. Demonstration zones set up within China are now functioning as live laboratories for foreign scientists, policymakers, and engineers who want to mimic China's success in their own countries. This proactive global outreach is an expression of China's larger vision of eco-diplomacy, in which environmental cooperation is a basis for more robust global partnerships. By converting its internal environmental challenges into opportunities for global cooperation, China is not only augmenting its geopolitical power, but also making a significant contribution to global sustainability. Its leadership in desertification management is a testament to the power of long-term policy planning, scientific innovation, and sharing solutions to transform environmental crises into a common development of the world. With the world watching and learning, the next big question is, can China's desert-fighting tech spark a global movement? Future outlook and global use. Looking ahead, the success of China's desert control robots holds significant potential for replication in other parts of the world, struggling with similar ecological challenges. Many countries in Africa, the Middle East, and Central Asia face accelerating desertification, driven by climate change, overgrazing, and land mismanagement. These regions often lack the infrastructure, labor capacity, or resources for large-scale manual afforestation, making robotic solutions a highly attractive alternative. Given the structural similarities between China's desert regions and those in nations like Saudi Arabia, Egypt, and Kazakhstan, the core technologies developed for China's environment could be adapted with minimal customization, unlocking a new global frontier in ecological restoration. To enable wider use, sustained innovation is concentrating on increasing the autonomy, reliability, and versatility of machines. Next-generation models are being engineered by developers with enhanced energy efficiency, extended battery life, and upgraded AI software, enabling robots to make more subtle judgments in the field. Even solar-powered systems are being designed to reduce the need for dependence on external charging facilities, important in remote, sun-bathed areas. More use of machine learning will also allow robots to adapt their strategies according to real-time climate and soil information, enhancing both seedling survival rates and planting precision. Such enhancements will render the systems more robust, particularly in regions with volatile weather patterns or variable, rugged terrain. China is also increasing its contribution to international ecological cooperation by streamlining models for collaboration that allow for sustainable global adoption. China is no longer simply exporting completed machines, but is now studying joint ventures, local manufacturing, and training mechanisms that enable other countries to drive and sustain the technology without Chinese intervention. By doing this, it guarantees foreign allies not just the machinery, but also the skills to handle long-term desertification control projects. Already, demonstration areas and pilots are being talked about with countries in the Sahel region and portions of Central Asia, where desertification is a dominant danger to agricultural food security and rural life. These forward-looking measures highlight China's changing role, not only as an environmental technology trailblazer, but as the world leader in enabling sustainable land management, in further refining dynamic, scalable, and affordable robot-based afforestation systems, and in making them available in mutually beneficial ways. China is positioning itself to introduce a new decade of global partnership in ecological rehabilitation. The future of international desertification management might just be determined as much by climate science and policy as by the humble, boots-on-the-ground abilities of autonomous technology to stem the tide of desertification tree by tree. A further important consideration for China's desert control robotics scalability worldwide is the increased convergence of international policy agendas towards climate resilience and sustainable development. As countries sign up to UNCCD and Paris Climate Accord targets in rising numbers, technologies that deliver scalable, quantifiable environmental outcomes are gaining appeal. Robot afforestation also finds itself squarely in this context, providing the link between policy and action. With international funding vehicles, like green climate funds and regional development grants, starting to fund nature-based solutions leveraged by technology, the financing environment becomes increasingly supportive of cross-border deployment of such systems. This alignment of political will, financing, and technological readiness greatly raises the chances of broad-scale adoption outside China itself. Thanks for watching. If you found this video fascinating, don't forget to like, drop a comment below with your thoughts, and subscribe to our channel for more unbelievable tech and environmental breakthroughs. And hey, don't go anywhere. Click the next video on your screen to see another incredible transformation you won't believe is real.